Welcome to The Explainer. Today, we're diving deep into something that honestly looks incredibly unremarkable. I mean, we're talking about a dull, heavy metal here. It doesn't glow in the dark like the movies want you to believe, and it definitely doesn't explode just because you touch it. Yet, paradoxically, hidden right inside the atomic structure of this completely ordinary-looking material is a world-changing, literally awe-inspiring amount of power. Yep, we're talking about enriched uranium.
So let's start with a pretty crucial question. What if I told you that an ordinary rock, just pulled straight from the dirt, held the power to completely reshape global energy, accelerate monumental scientific discoveries, and at the exact same time, become the core component of the most destructive weapons humanity has ever engineered? Like, how can a material that seems so completely inert contain such an extraordinary amount of latent energy?
To answer that, here's our roadmap for today. First, we'll hit the science of uranium. Next, decoding enrichment, followed by the power of fission and atomic history. And finally, we'll wrap up by looking at powering the modern world and global security. All right, Section 1, the science of uranium. So, uranium is a naturally occurring chemical element. You can find it in rocks, soil, even in seawater. On the periodic table, it's represented by the symbol U, and it sits right at number 92. Now, that atomic number is absolutely essential because it means every single uranium atom contains exactly 92 protons in its nucleus, and that makes it, amazingly, one of the heaviest naturally occurring elements on planet Earth. But here's the kicker. When we dig it out of the ground, it's not just one uniform type of atom. It's actually a mixture of different isotopes. Natural uranium is almost entirely made up of the isotope uranium-238. We're talking nearly 99% of it. But there is a tiny, incredibly important 1% sliver left over, and that tiny sliver is uranium-235.
So why do we care so much about that tiny sliver? Well, because uranium-235 has a very special nuclear property. Under the exact right conditions, its nucleus can undergo nuclear fission. When a U-235 nucleus splits, it releases massive energy and produces additional particles. These particles can then bounce off and interact with other uranium nuclei, potentially triggering a continuous self-sustaining nuclear reaction. It's like a microscopic domino effect. And this exact scientific phenomenon is the beating heart of both nuclear reactors and nuclear weapons.
Moving right along to Section 2, decoding the enrichment process. Now, you might be wondering, what does it actually mean to enrich this stuff? Well, enriching uranium doesn't mean making it more radioactive by adding some glowing green chemical to it. To really understand enrichment, imagine sorting a jar filled with thousands of white balls, representing uranium-238, and only a tiny, tiny handful of red balls, representing uranium-235. Enriching the mixture simply means increasing the concentration of those red balls. You're really just changing the ratio so that the highly reactive U-235 is way more prominent in the mix. But here is the catch, and it's a big one. This separation is incredibly difficult. Because U-238 and U-235 are both uranium, they are chemically identical. They behave the exact same way in chemical reactions. You can't just mix in a solvent to separate them. Instead, engineers have to rely on the tiny, microscopic difference in their physical mass. This requires highly complex, astronomically expensive, and incredibly energy-intensive industrial technologies to literally spin and filter the atoms purely by their weight. It is a massive undertaking.
Okay, Section 3, the power of nuclear fission.
So what's the payoff for all that effort? It's all about energy density. Look, when we burn conventional fuel like gasoline or coal, the energy released comes merely from rearranging the chemical bonds between atoms. But nuclear fission? It is an entirely different beast. The energy from fission comes from violent changes inside the atomic nucleus itself. Because of this, a remarkably small amount of enriched nuclear fuel contains vastly, vastly more energy than huge amounts of conventional fuel. Let's pivot a bit for Section 4, a history of atomic power. The history of atomic power reveals this really dramatic and rapid shift in human capability. We start with the early discoveries of radioactivity, where scientists first realized atoms weren't indivisible. That realization led to massive breakthroughs in the 1930s regarding nuclear fission. Then, during World War II, this research became a completely urgent military priority. That culminated in the creation of nuclear weapons, which, as we know, demonstrated a terrifying new scale of destructive power. However, after the war, global attention increasingly expanded toward peaceful applications, leading to the dawn of post-war commercial nuclear power generation. That brings us right to Section 5, powering the modern world.
It's actually kind of fascinating how conceptually simple a nuclear reactor is at its core. I mean, the extraordinary, intense heat generated from the atomic fission of enriched uranium is simply used to heat water. That boiling water produces high-pressure steam. The steam then turns massive conventional turbines, and those spinning turbines generate the electricity that powers our homes and our cities. So, while the heat source is incredibly futuristic and atomic, the actual method of generating electricity, it's fundamentally similar to a traditional coal or gas plant. Kind of wild, right?
Of course, we have to impartially weigh the realities of this technology, especially since it remains a topic of intense global debate. On the pro side, nuclear plants offer immense energy density. They can run continuously for really long periods, and they produce very low direct carbon dioxide emissions during operation. But on the con side, the technology is astronomically expensive to build. It requires highly complex safety systems, and societies have to figure out long-term secure management for the radioactive waste it leaves behind. It's a real trade-off. And finally, Section 6, global monitoring and security.
This dual nature makes enriched uranium one of the absolute most sensitive subjects in international diplomacy. International organizations, prominently the International Atomic Energy Agency, or IAEA, play a totally crucial role here. They use rigorous international safeguards. We're talking on-the-ground inspections, incredibly detailed accounting systems, and constant surveillance to meticulously track nuclear materials. It's this super delicate global balancing act, allowing nations to pursue peaceful nuclear energy and medical research while strictly preventing the proliferation of nuclear weapons. So, as we wrap up our explainer today, we really have to look at the massive responsibilities that come with utilizing enriched uranium. Managing this material safely requires preventing catastrophic accidents through multi-layered safety systems, engineering secure long-term storage for radioactive waste, halting international proliferation, and, crucially, maintaining public trust through transparent and responsible leadership. Ultimately, the story of enriched uranium leaves us with this pretty profound realization. As humanity has learned to peer inside the atom and release the spectacular energy hidden within, we are entirely responsible for how that knowledge is used. Literally, a tiny difference in an isotope's concentration dictates whether this material lights up an entire city or threatens its very existence. It really leaves us with a critical question to ponder. As our scientific knowledge continues to advance into the unknown, are we truly prepared to manage the immense power we've unlocked from the tiniest building blocks of our universe?